If you double every entry of a 3 by 3 matrix, you might expect the determinant to double as well, but it does not. It actually multiplies by 8. The determinant of 2a equals 2 cubed times the determinant of a, which is 8 times the determinant of a. That factor of 8 is not a quirk. It follows from one of the most powerful properties that determinants have. More generally, for an n by n matrix, scaling every entry by a constant c multiplies the determinant by c to the n. You'll also discover that rows and columns are secretly interchangeable when it comes to determinants. That 2 to the n factor comes from a single foundational property. Let's start there. Property 9, the multiplicative property. For any two n by n matrices, A and B, the determinant of their product AB equals the determinant of A times the determinant of B. This is a powerful result. It converts matrix multiplication, which is a complex operation, into simple scalar multiplication of the determinants. However, here is one critical warning. Determinants do not respect addition. The determinant of A plus B does not equal the determinant of A plus the determinant of B. Let's see a quick counterexample to prove this. Set A and B both equal to the 2 by 2 identity matrix. Then A plus B equals 2 times the identity matrix. The determinant of 2 times the identity is 2 squared times the determinant of the identity, which equals 4 times 1, giving us 4. But the determinant of A plus the determinant of B equals 1 plus 1, which is just 2. 4 does not equal 2. So the takeaway is clear. Multiplication works with determinants, but addition does not. Let's verify this property with a concrete example. Take A as the 2 by 2 matrix with rows 2, 1, and 0, 3. Take B as the matrix with rows 1, 4, and 2, 1. The product AB gives us the matrix with rows 4, 9, and 6, 3. Now let's compute each determinant. The determinant of A equals 2 times 3 minus 1 times 0, which equals 6. The determinant of B equals 1 times 1 minus 4 times 2, which equals negative 7. The determinant of AB equals 4 times 3 minus 9 times 6. That's 12 minus 54, which equals negative 42. Now let's check. 6 times negative 7 equals negative 42. That matches the determinant of AB exactly. So the multiplicative property holds perfectly in this example. The multiplicative property yields immediate consequences. First, let's find the determinant of an inverse matrix. Start from the defining equation. Inverse times A equals the identity matrix I. Now take determinants of both sides. The left side becomes the determinant of A inverse times A, which equals the determinant of I. By the multiplicative property, the left side splits into the determinant of A inverse times the determinant of A. On the right side, the determinant of I equals 1, since I is a triangular matrix with all ones on its diagonal. And the determinant of a triangular matrix is the product of its diagonal entries. So we have the determinant of A inverse times the determinant of A equals 1. Dividing both sides by the determinant of A, we get our main result. The determinant of A inverse equals 1 over the determinant of A. Notice the self-consistency here. This formula requires the determinant of A to be non-zero, since we cannot divide by 0. And a non-zero determinant is exactly the condition for A to be invertible in the first place. As a quick example, if the determinant of A equals 5, then the determinant of A inverse equals 1/5. Second consequence, powers. And the determinant of A squared equals the determinant of A times A. By the multiplicative property, that's the determinant of A times the determinant of A, which equals the determinant of A quantity squared. More generally, the determinant of A to the k equals the determinant of A raised to the k. Now let's look at the scaling result. For an n by n matrix, multiplying by 2 multiplies every row by 2. Our scalar row property says that pulling a factor of 2 from one row multiplies the determinant by 2. With n rows, we pull out n factors of 2. So the determinant of 2a equals 2 to the n times the determinant of a. For a 3 by 3 matrix, 2 cubed is 8. So we get 8 times the determinant of a. And more generally, for any scalar c, the determinant of c times a equals c to the n times the determinant of a. The 2 to the n factor has a clean geometric interpretation. The determinant measures sine volume in 3 dimensions, start with a unit cube, side length 1, volume 1. Now double every axis. The x-axis doubles, the y-axis doubles, and the z-axis doubles. The cube becomes 2 by 2 by 2, with volume 2 cubed equals 8. Each dimension contributes one factor of 2 in n dimensions. Doubling every axis multiplies the volume by 2 to the n. So the determinant of 2a can be written as 3 factors of 2, 1 red factor of 2 for the x-axis, 1 green factor of 2 for the y-axis, and 1 blue factor of 2 for the z-axis, all times the determinant of a. This simplifies to 2 cubed times the determinant of a, which equals 8 times the determinant of a. More generally, for any scalar c, the determinant of c times a equals c to the n times the determinant of a. Determinants play nicely with products. Now let's look at a second property, equally powerful. This one is about the transpose. A quick reminder, transposing a matrix means its rows become columns and its columns become rows. Property 10 states the determinant of A transpose equals the determinant of A. The determinant is completely unchanged by transposition. Here's the proof using LU factorization. Recall that any invertible matrix A can be factored as L times U, where L is a lower triangular matrix with 1s on its diagonal, and U is an upper triangular matrix. Now transpose both sides. A transpose equals the transpose of L times U. When we transpose a product, the order reverses. So A transpose equals U transpose times L transpose. Notice what happens to the shapes. U transpose, which was upper triangular, is now lower triangular. And L transpose, which was lower triangular, with 1s on the diagonal, is now upper triangular with 1s still on the diagonal. Now let's track the determinants through each factor. L is lower triangular with 1s on the diagonal, so the determinant of L equals 1. L transpose is upper triangular with the same 1s on the diagonal, so the determinant of L transpose also equals 1. U is upper triangular, so its determinant is simply the product of its diagonal entries. U transpose is lower triangular with exactly the same diagonal entries, so the determinant of U transpose equals the determinant of U. Now we apply the multiplicative property of determinants. The determinant of A equals the determinant of L times the determinant of U, which is 1 times the determinant of U, which simplifies to just the determinant of U. The determinant of A transpose equals the determinant of U transpose times the determinant of L transpose, which is the determinant of U times 1, which also simplifies to the determinant of U. Both expressions equal the determinant of U. Therefore, the determinant of A transpose equals the determinant of A, and the proof is complete. Here's the payoff of the transpose property. Since the determinant of A transpose equals the determinant of A, every row property automatically holds for columns too. The reasoning is elegant. Any column operation on A is the same as the corresponding row operation on A transpose, and the determinant doesn't notice the transpose. This gives us 3 column rules, completely free of charge. Let's see them side by side. First, a matrix with a 0 row has determinant 0. The column twin, a matrix with a 0 column, also has determinant 0. Second, swapping 2 rows flips the sign of the determinant. The column twin, swapping 2 columns also flips the sign. Third, the determinant is linear in each row separately. The column twin, the determinant is linear in each column separately. Every row rule has a column twin, and the bridge between them is the transpose property. A column operation on A equals a row operation on A transpose, and the determinant of A transpose equals the determinant of A. Two properties, enormous reach. The multiplicative property states that the determinant of A times B equals the determinant of A multiplied by the determinant of B. This single identity bridges matrix algebra and ordinary arithmetic, and it yields powerful formulas. First, the determinant of A inverse equals 1 over the determinant of A. To see why, know that A times A inverse is the identity, so applying the multiplicative property gives determinant of A times determinant of A inverse equals 1. Second, the determinant of A to the kth power equals the determinant of A all raised to the kth power. Just apply the multiplicative property repeatedly. Third, the determinant of C times A, where C is a scalar and A is n by n, equals C to the n times the determinant of A, because scaling the entire matrix scales each of the n rows by C. The transpose property states that the determinant of A transpose equals the determinant of A. This guarantees complete row-column symmetry, effectively doubling our toolkit. Whenever a theorem holds for rows, it automatically holds for columns as well. Together, these two properties form the algebraic backbone of determinant theory. Whenever you encounter a product of matrices, break the determinant apart using the multiplicative property. And whenever someone proves a raw result, the column version comes free, thanks to the transpose property.